Okay, so let's take the next one, which is strong versus eventual consistency. Strong consistency. Strong consistency where all users see the updates immediately. So all users see the updates immediately. Slower. Less available. Strong. Eventual consistency. Write event, read event. Eventual consistency is where updates are spread over time. High availability. Strong consistency is where all users see the updates immediately. Strong consistency, but less available. It is slower and less available. Eventual consistency. Okay, let me check proper simpler definition. Strong versus eventual consistency. Let me add a comment or text. This is not great. Use experience, but let me put that in a separate note. With the core trade-off, consistency versus availability versus latency. Okay, this looks good. Small. Acid versus base. Transactional contract. Guarantees versus realities. This is important. Atomicity, consistency, isolation, durability. Basically available. Soft state, eventual consistency. Financial systems, asset properties, inventory, strong consistency. Prioritize availability. A verbal agreement. Large-scale distributed systems. Social media feeds analytics. Prioritizes availability. Inside, in practice, many architectures combine both. Many architectures combined both. Interesting. Acid for the core money flows and base for things like feeds and analytics. Strict data integrity versus high availability and performance. Okay. Gardening is managing incoming traffic. Domain name system. This maps human readable domain names to server IP addresses. CDN. A network distributed server that cache static content closer to users to reduce latency and offload origin servers. Load balancer spreads incoming traffic. multiple servers to prevent overload and remove, improve reliability. Round robin, least connections, IP hash. Round robin, least connections, IP hash, API gateway, single entry point for all API calls, handles routing, rate limiting, authentication, and login access. Specialized reverse proxy for microservices, reverse proxy. Core trade-off, centralized control versus performance versus potential bottlenecks. Regarding the gates, DNS, CDN, load balancer, and API gateway. Okay. Lines of communication using the right protocol. REST versus gRPC, service to service. Uses HTTP with JSON. HTTP, while gRPC uses HTTP2 with JSON. Simple, human readable, great for public APIs. And then gRPC with take a break. Okay, we are back. Attending the call. Lines of communication, choosing the right protocol. REST versus gRPC. REST uses HTTP, gRPC uses HTTP2. Binary messages, smaller, faster, strongly typed. Preferred for internal microservice communications where performance is critical. The performance would be the keyword, and also internal microservice communication, gRPC. Comparison of TCP versus UDP, the transport layer. TCP, reliable, connection-oriented, guarantees auto check delivery used for web pages, APIs, file transfers. Registered mail. UDP, connectionless. Hospital does not guarantee delivery. Video calls and gaming, UDP. Web pages, APIs, file transfer. Connection oriented, guarantees. Reliable, I think might be the keyword here. Reliable, TCP versus UDP. UDP. HTTP 2, HTTP 3 are modern evolutions designed to reduce latency by multiplexing requests over a single connection or using UDP. Quoted of performance and efficiency versus simplicity and compatibility. Okay, let's move on. Keeping the system in sync, real-time and decentralized updates for server to client push WebSockets. Full duplex connection, where client and server can send messages anytime, ideal for chat chat, live collaboration, multiplayer games, collaboration. Okay, we have server sent events, SSE, one-way channel for the server to push updates. Okay, push updates to clients, one-way channel, simple and WebSockets, perfect for live score updates and notifications. Okay, live score updates and notifications. Notifications. Okay, live score updates and notifications. Long polling, a simulated push where the client request is held open by a server until there is no new data. A less efficient but highly compatible fallback. Simulated push. Long polling. Real-time freshness versus implementation complexity and reduced overhead. Okay, from server to server. For server to server, state sharing, gossip protocol, nodes share information, spreading information like gossip, fault tolerant discovery helps citizen configuration in large dynamic clusters without central authority. Nodes share information by talking to random peers, used for fault tolerant discovery, health status, configuration in large dynamic clusters without a central authority. Health status. Okay, let's move on to the next item, which is scaling the data vault. Scaling the data vault, managing data across machines, sharding. Concept sharding, which is data partitioning. Shard key, critical for event distribution. Shard key. Shard 1, 2, 3, 4. What? Splitting a large database into smaller, faster, more manageable parts called shards. Splitting a large database into shards. Choosing a good shard key. Shard key is critical to avoid hotspots where one shard gets most of the traffic. Shard keys. And then data partitioning is data copying, data partitioning and data copying, replication, write master, read slave. What? Keeping multiple copies of data on different nodes for availability and read performance. Replication. Multiple copies on different nodes for availability and performance. Data replication. Data copy. Okay. Patterns: master slave, master. One write, multiple reads, multiple writes, conflict reconciliation. Okay. Patterns. Okay. Third one, consistent hashing. Consistent hashing, or a smart distribution technique that minimizes data movement when nodes are added or removed from a cluster. Essential for distributed caches and databases where the cluster size changes frequently. Okay. Smart distribution technique that minimizes data movement. Okay, minimizes data movement when nodes are added or removed from a cluster. Okay, go to the next one. Optimizing the vault. Faster data access internals, Indexing B-trees, faster data access, data structures. I think this is indexing B-trees versus LSM trees. B-trees excellent for read heavy workloads. B-trees. Indexing maintains sorted data for fast lookups, insertions, and deletions, optimized for reading. Read heavy workloads, optimized for reading. B trees, LSM trees, right? Excellent for write heavy workloads. LSM trees are write heavy workloads. Right, fast in memory, asynchronously merged to disk segments, optimized for writing. B trees versus LSM trees. Okay, and then data structure normalization versus denormalization. It's optimized for writes, reads, redundancy. Data is split into separate linked tables to eliminate duplication. Optimized for writes, reduces normalization versus denormalization. Optimized for writes, optimized for reads. Data is split into separate linked tables to eliminate duplication. Data is combined into fewer wider tables, faster reads but increases redundancy. But the third one, efficiency trick, Bloom filters. Probabilistic data structure that quickly answers, might this item be in the set? Bloom filters. Might this item be in the set? The no false negatives. Avoid expensive disk or network lookups for items that definitely don't exist. A fast gatekeeper that is definitely not, or maybe. A fast gatekeeper that says definitely not, or maybe. Avoids expensive disk or network lookups. Okay, code. Let's move on to the next one, which is modern data strategy, the right tool for the job. Application logic, relational database, DB for transactions, key value store for caching, document store for flexible schema, graph DB for relationships. Using multiple database technology within the same system, each chosen from specific strengths, trade-off increased power and flexibility, which is higher operational complexity. Here, a few things to note: asset, key value store, and then for caching, document store, flexible schemas, graph DB, relationships. Emerging trend, vector databases. Embedding model, CAD. Okay, what database is designed to store and query high dimensional vectors. Vector DB. Power similarity search instead of exact matches. Similarity search instead of exact matches. Whiteboard, essential for modern AI search and recommendation systems. Vector DB, vector database. Modern AI search and recommendation systems. AI search recommendation systems. Vector database. So the next one, which is a building the future part 1. Proactive defensive maneuvers. Rate limiting pattern 1. Or rate limiting controls how many requests a user or service can make in a time window. Because users can make in a time window. Protects against abuse, traffic spikes, and unavailable safety break for shared resources. Safety break, rate limiting, circuit breaker. Monitors call to a remote service. If failure exceeds threshold, circuit opens and fails your request immediately without even a single failing service. From drawing down its callers in a cascade of timeouts. Cascade. Circuit breaker. Threshold. After threshold, the circuit opens. And then pattern 1 is the rate limiting. And then you have this circuit breaker, which opens the circuit after threshold, preventing cascadal failures. And then pattern 3, bulkhead. What is this bulkhead? Okay, so isolates system components. So its failure area is contained. Bulkhead, compartment 1, compartment 2, then failure. Like a bulkhead in a ship that contains flooding to one compartment. It limits the blast radius of a failure. Building for failure part 1, proactive defensive maneuvers. Trade-off resilience and fault isolation versus added complexity and configuration. Let's move on to the next one, which is part 2, building for failure part 2, graceful recovery patterns. Very important. Graceful recovery patterns. Graceful recovery. Pattern 1, retrace with exponential backoff. Pattern 2, idempotency. Pattern 3, saga pattern for distributed transactions. Retrace with exponential backoff. What is the retrace with exponential backoff? Fail, and then retrace exponential backoff plus jitter. When operation fails, try again, but wait longer between each subsequent attempts. Try again, but wait longer between each successive attempt. Add jitter to avoid thundering herds. And then jitter. Interesting. Why? Recovers from transient errors without overwhelming a studying service. Retrace without backoff can make outages worse. Retrace with exponential backoff. Pattern to idempotency. Same effect. It has same effect whether it's performed once or multiple times. Idempotency. Critical for making retrace safe. Prevents issues like double charging. A customer if a payment request is retried. APIs often use an idempotency key header. Okay, pattern 3, saga pattern. Saga pattern. Now, where is the saga pattern? Saga pattern. Order created, payment successful. Cancel order, refund payments. Cancel order, refund payment, shipment fails. Okay, a sequence of local transactions where each step publishes an event to trigger the next. If a step fails, compensating actions are run to undo previous steps. Okay, compensating actions are run. Interesting part is compensating actions are run. If a step fails, manages workflows across microservices without blocking and tight coupling of two-phase commit. Saga pattern for distributed transactions. A sequence of local transactions where each step publishes an event. Now let me share the short video. Okay. Manage workload multiple. Okay, let's move on. Decoupling for speed and resistance, caching and queues. Caching store frequent access data in a fast remote layer, memory layer, send backend load. Cache assigned right through eviction policies. Least frequently used hard problem. Cache invalidation is famously difficult. And then messaging, point-to-point, pubs up. Message queues point-to-point, to-do list. Because obviously decouple central receiver to asynchronous work. Pubs up. Broadcast style. Okay, so here to-do list, basic point-to-point. This is done in broadcast style. Pubs up, publish, subscribe, dead letter queues. Holding area for messages that fail. Crossing preventing them from blocking the main queue. Performance, decoupling versus data freshness and consistency challenges. Okay, we come to the last slide. This the architect's compass, key takeaways. Operate with insight and security. System is only as good as your ability to run it. Observability, use distributed tracing to understand request flows, define your SLIs, SLOs, and SLS to measure reliability. Security, assume never trust, always verify stands with zero trust. Distributed tracing, SLIs, SLOs, SLAs, zero trust, OAuth 2.0, so TLS, encrypt everything in transit. And then design is about trade-offs. There is no best solution. Every choice is a balance. Consistency versus availability, latency versus throughput, simplicity versus flexibility. Failure is normal. Plan for it. Failure. Plan for it. Distributed systems, things will fail. Build resilience from the start. With patterns, different patterns which we have seen. No best solution. Okay, that was another call towards the end. But yeah, decouple for performance and scale. Caching message queues. Observe are your best friends. They break dependencies, absorb spikes, and improve responsiveness. Okay, let's quickly recap what all we have seen. Very short primer to system design. Okay, we have seen the foundation, but understanding what is a monolith, microservices, what is the stateful and stateless architecture, and then scaling, horizontal, vertical scaling, and then along with it, Amdahl's law. And then the laws of distributed physics, cap theorem, consistency, availability, partitioning, and then EAC, LC. Hassel C theorem with latency here is one more parameter is added, and then strong versus eventual consistency. Updates spread over time. Updates immediately. Updates spread over time. Then acid versus base, guarantees versus realities. Okay, guarding the gates. How do we manage incoming traffic? DNS CDN load balancer API gateway, and then protocols. Just a glimpse into what are these protocols, and then real-time decentralized updates, keeping the system in sync. Sockets, server sent events, long polling, gossip protocol, scaling the data work, managing data across machines, sharding, replication, consistent hashing. Then we looked at optimizing the vault, faster data access internals, B trees versus SL trees, data structure, normalization versus denormalization, joins, blue filters, and then polyglot persistence, different types of technologies. Then vector databases, designed to store and query high dimensional vectors, or similarity search instead of exact matches, similarity search, AI search recommendation systems. Then rate limiting circuit breaker bulkhead, how do we control failures, proactive defensive maneuvers, graceful recovery patterns, retries with exponential backups, idempotency, saga pattern. And then decoupling, caching and messaging, and then we concluded with this. Great, thank you for following along, and I'll see you in the next videos. And then just to give a glimpse, and coming videos would be more technically inclined in software engineering, computer science, fundamental concepts, various technicalities, and best engineering practices. We'll focus there. Let's learn together. Thank you.